Okay, welcome to this session, potential application for future satellite missions for public health. I'm the moderator, Bryan, Duncan. I'm a HAQAST member. And we have four great speakers. The first is Rob Levy of NASA Goddard Space Flight Center. So I'll let him take it away.
I don't know if I'm a great speaker, so I'm sorry. I'm a great person. Thank you. Okay, it's on. Thank you. Oh, okay, I gotta make it start. So yeah, just to introduce myself. I'm Rob Levy. I'm at NASA Goddard. Just a little bit about me and what I've been doing since 1998. I've helped develop and now maintain what we call the dark target aerosol retrieval algorithm, which includes products of aerosol optical depths. And one thing we do in our work is we do have a lot of users. So trying to appreciate that we have lots of user communities and trying to do our best to tell about strengths and weaknesses in our products. And I just wanted to say this because it's not just air quality, which is of course a huge important, but our products also are important because aerosols affect visibility, clouds and precip, chemical cycles, roles in biology, impact the radio budget. Of course, those are big ones. They're natural and man-made. They're inhomogeneous in space and time, and their distributions are always changing. So it's really an interdisciplinary thing, and we're kind of doing our best to be part of that. So I'm involved, or at least tangentially involved with the current HAQAST because I work with Pawan Gupta, who's now at Goddard and helping to lead the AeroNet team. And so we're part of this paper to incorporate satellite data updates into Air Now. And that project, I guess, officially had a closeout a couple weeks ago. So I think, so the next slide is kind of a summary of that. What Pawan wanted to be, because I'm pretty much doing my best to represent Pawan here as well, since he was the lead of that project. Basically, a summary was that the goes east and west, the NOAA products, were geographically weighted regression to get PM 2.5, and they're combined together to get the best spatial resolution. They worked on independent validation and error characterization. Part of the project was to add a deep learning algorithm to add value and to do some bias correction. And the whole project is discussed in its processing, integration, and visualization framework, and all the technical stuff is under preparation. And so the idea of that project was essentially to take the products from the satellites, have a whole bunch of steps, and do best to come out with hourly and daily PM 2.5. And it was many meetings. It was very interesting, and but how I got into it is my interest was in trying to join together multiple satellite products. And so we have this one algorithm that we use, and there's of course many other satellite algorithms out there too, but ours being what we call dark target is fairly simple, and we can apply it to many different sensors as consistently as possible. So the idea is that if you combine them together, every half an hour, what do you see for Terra? What do you see from Aqua? Beers. We also had access to Emory data, goes east and goes west. So you essentially get, more filled in global pictures than you would with one sensor alone. And since it's a consistent algorithm, we hope that the biases and everything else would be fairly consistent from sensor to sensor. And so the idea of, that we would like to see is that this kind of framework and the implementation, might serve as guidelines for upcoming missions. So, how do you add in tempo, pace, MAIA, and then GeoXO and beyond into this kind of comprehensive data set? In other words, more sensors, less holes. That's what I said down here. And so, but again, from my interest too, is I'm also interested in long-term data records. And so going back in time, so we have MODIS that was, started in 2000. We have MODIS Terra and Aqua. We're kind of trying to take that data record and continue it with years. Taking some effort. I think we're getting to the point that we can believe long-term time series from sensor to sensor and connect them together. So basically, we're getting to the point with not just our algorithm, but multiple algorithms on these kind of imagers that we are getting into climate data record quality for resolution, accuracy, stability, time length. Of course, what's missing, the temporal resolution, which we are getting from the geo. And what's cool is that, so, obviously Tempo just launched. There's also the Mediasat third generation is now up in Europe, from Europe. And so you do get, we're now getting what we call a LEO, kind of a geo ring of these sensors all over the globe, and they're overlapping. So you can actually track things. Eventually, we'll be able to track things all around the globe with no gaps, which is pretty cool. And the international community is working on coordination that puts them all in the same cadence, and all will contribute to aerosols and clouds research. Also, from the NASA speak, also contribute to the program of record, so like synergy with new observations from the, let's say, the NASA atmosphere observing system that was discussed yesterday. But again, the hard part is requiring a new strategy and organizing that information system. Like, there's going to be a lot of data. Also, this is kind of cool. This was fun for me, and it led to it also added to a paper that Amy Huff from NOAA added. And I just thought, it's not just global. When you have the geos, you can track. And this is, of course, this is a bunch of purple layers in the DC metro area on the left here, overlaid with GOES imagery. Play it one more time. And you can see the smoke from this is a prescribed burn in Quantico, and how the numbers are not right. I didn't use the right, what do you call it? Correction factor for the purple layers. But you get the idea that, for the even local small scale events, you look at the combination of the surface and the satellite, you can see them happening. And so I just wanted to say in summary that the future is kind of now. Tempo just launched, joining GEMS. We have Tropomi and OMI, HAQAST next year. HAQAST also has these polar emitters, which will do cool things. MAIA, which was talked about a little bit. There's also the high resolution sensors such as Landsat and Sentinel-2. And then I guess there's this burgeoning community of commercial satellites at even higher resolution, some which have imaging and capabilities that we can use for monitoring aerosols and PM. The atmospheric observing system, GeoXO, and all the international things that we can get our hands on. And so it's kind of crazy just how much information will be around in the next few years to work on these problems. So that was what I wanted to chat about. So hopefully I don't know what time was. Perfect. All right. Perfect.
Okay, we're going to hold questions to the end. So Yang Lu, you're up. Yang Lu of Emory University, the HAQAST member as well.
Hi, everyone. I'd like to take this opportunity to provide a status update for the MAIA mission. I borrow most of the slides from the MAIA PI, Dave Diner from JPL, and made some modifications. So MAIA is a EBI-3 mission. It was selected in 2016 with the primary selling point of societal benefits. In particular, MAIA will explore the linkages between exposure to different particle types and human health. And here we didn't say composition or chemical constituency, because types is a little bit more inclusive, includes the shape, the size, light, scattering, absorption properties, and inferred chemical composition. Okay, and MAIA is a pretty interesting mission because it has a shadow mission. There's a very intensive ground component and then a very dedicated chemical model simulation component built into the mission. And so MAIA is not only a satellite instrument. It has its own dedicated surface monitoring network, dedicated chemical transfer model, in this case, WRF-Chem simulations for all the primary target areas, and then dedicated ground teams of epidemiologists in all the primary target areas committed to conduct air pollution epidemiology study using MAIA-powered exposure estimates. So it's quite a scene if you're interested in sitting in MAIA science team meetings, okay? Listening to JPL engineers talking to environmental epi people. And the MAIA is not a global mapper. It's a targeted instrument, meaning MAIA would only collect information in selected global sites. And these sites are tiered. The first tier is called the primary target areas, or PTA. Usually these are larger urban centers around the world that requires MAIA to take samples on average 3.5 times per week. And then these sites must have a dedicated team on the ground with access to health data in these locations. Each location is about 150,000 square kilometers. Right? So it's quite a large metropolitan area. And then there are currently 11 PTAs around the world. There are secondary target areas. These are areas where MAIA would only retrieve aerosol optical properties as their operational products. So over the STAs, there will be no PM products. However, the aerosol products are inputs of the PM products. If you have a ground monitor network, not as part of the MAIA mission, but you do have ground observations, you can take advantage of the MAIA retrievals over these areas and create your own PM products. Okay? It's just, you can't call it the official MAIA product. And then of course, there are calibration and validation target areas. Over the primary target areas, we will provide, or the MAIA mission will provide daily average total PM10, total PM 2.5 mass, and speciated PM 2.5 mass concentrations at 1 kilometer spatial resolution every day, either available with successful AOD retrievals and gap filled with chemical transfer model simulations. Okay. This table is a little busy, but it actually lists all the current PTAs and then their proposed health effects studies. So for example, in Georgia, we will use ED visit data to study the respiratory morbidity outcomes due to particle exposure. That's acute effects. For New England PTA, they will cover from acute effects to subchronic effects all the way to chronic effects. So, heart attack, stroke, birth outcomes, all the way to mortality. The latest mission update, so NASA has partnered with the Italian Space Agency to form a joint mission. So there is the, what do we call it? NASA MAIA or MAIA, EBI MAIA, and then the ESA MAIA mission, okay? And this is a 3-year baseline mission to be launched in either late 2024 or early 2025. And the ground monitoring network is already almost up and running in all the PTAs. And this is the ground mission is a partnership with Department of State, USAID, and many other international collaborators. And if you have any questions about the MAIA mission, its products, feel free to contact me or contact Dave. Thanks.
Hey, thank you, Yang. Our next speaker is Leticia Nogueira. She's from the American Cancer Society, and she's also a HAQAST ambassador.
Yes, I'm Leticia Nogueira. I'm a researcher at the American Cancer Society, and I'm the NIH Climate and Health Scholar hosted by the National Cancer Institute and a HAQAST ambassador. And I work mainly on health disparities that can be addressed by policy change, especially climate change and structural racism. So Hurricane Harvey was when climate change and cancer collided for me. I was working at the Texas State Health Department at the time, and I was able to see firsthand how these climate-driven disasters can impact the health of communities. Let me explain. Climate change alters the behavior of extreme weather events. Warmer air holds more water vapor, which increases the water capacity of hurricanes. And we could see this with Hurricane Harvey. This is a map from NOAA showing rainfall over Houston during Hurricane Harvey. And I hear that NOAA had to add new colors to the legend because it had never rained so much in one spot before. Now, here's the thing. It wasn't the first time Houston had been impacted by a hurricane. The hospitals thought they were prepared. They all had backup generators, but Harvey was different. It stalled over Houston. Then it rained. Then it flooded. Then the backup generators flooded. Extreme weather events can damage medical infrastructure, break transportation links, disrupt supply chains, and interrupt access to care. That is especially concerning for medically vulnerable populations who need uninterrupted access to care, such as cancer patients. And the changing frequency and behavior of extreme weather events makes it harder for communities to prepare and respond to increasingly unpredictable circumstances. Soon after working on the response to Harvey, I joined the American Cancer Society, and the very first study I proposed was to evaluate the impact of hurricanes on cancer patients. And when I did that, people started laughing. Hurricanes and cancer, what are you talking about? So it took some convincing, but in the end, we did run this study, which sadly, but unsurprisingly found that individuals whose facility was impacted by a hurricane during their radiation treatment had worse overall survival than similar patients who completed treatment at the same facility, but in the absence of disasters. And for this study, we ended up using FEMA data. We had considered using NOAA data, which had detailed information on precipitation. However, FEMA data was a better proxy for the impacts that the hurricane had on the community. The longer the FEMA disaster declaration lasted, the worse the overall survival in that population. But here's the thing. This is what emergency power generators look like when they work. We measure the health consequences of climate-driven disasters that were due to disruption in access to care, but there are also environmental exposures associated with emergency preparedness and response efforts, which are modifiable. Pollution from emergency generators are a public health issue, and so far our understanding is mainly coming from deaths from carbon monoxide poisoning. Understanding the longer-term consequences of diesel emergency generators is important because with climate-driven disasters, localities can become dependent on emergency generators for long periods of time. That's what happened in Puerto Rico. After Maria, it took 11 months for PREPA, the Puerto Rico Power Authority, to restore power. And healthcare facilities had to rely on emergency diesel generators for almost 2 months. The demand for diesel-generated electricity was so high in Puerto Rico that EPA issued a waiver and allowed burning of sulfur-containing diesel in Puerto Rico. So here's my question. Once the storm has passed, is measuring how air quality changes as power is restored satelliteable? Because another thing I learned while working on the response to Hurricane Harvey was that TCEQ brought air quality monitoring equipment inside before the hurricane hit, because the storm can damage the equipment. And yesterday I learned that 80% of counties in the US don't have air monitors. So using on the ground air quality monitors for evaluating exposure to pollution in the aftermath of disaster is not ideal. Satellite data, I found, is already being used to evaluate electricity restoration using light at night after disasters. And yesterday there was a question about how to figure out what satellite measures or what studies we can do that are relevant for communities and for policymakers. And this question is timely because CMS just issued a categorical waiver that allows healthcare facilities to use emergency power sources that do not rely on diesel. So it has policy implications. Again, it's a modifiable factor. And while attending the NIH Climate and Health Scholars meeting a couple of weeks ago, I kept being asked, can we measure the health co-benefits of climate mitigation policies? Such as the one from CMS and also the Inflation Reduction Act, because that aims at reducing pollution from several different sources, because emergency power sources are not the only source of pollution I witnessed while working on the response to Hurricane Harvey. Hurricane Harvey's unprecedented precipitation, which climate change made 3.5 times more likely to happen, flooded chemical plants, oil refineries, and Superfund sites that released vast amount of carcinogens into the Houston community. And when you think about this, where are these carcinogens coming from? Our reliance on fossil fuels is a shared cause of climate change and an increasing exposure to carcinogens. When you realize this, one of the first examples that might come to mind is air pollution from vehicle emissions and lung cancer. The same air pollution that's driving the greenhouse effect also increases lung cancer risk. However, extracting, processing, transporting, and waste management of fossil fuels releases many carcinogens in the environment before and after they are consumed. Take fracking, which is used to extract natural gas, for example. In addition to the methane that is released at the wells, the compressor stations emit fine particulate matter, benzene, formaldehyde, and other non-human carcinogens, which I hear we might be able to measure now with temporal. Then there is the waste that flows back up a fracked well, which also contains carcinogens and is transported by large diesel vehicles, which increase pollution in neighboring areas, to injection wells where the waste is dumped and can contaminate water sources. These exposures can be extremely high in the aftermath of disasters, but low-grade long-term exposures also have health consequences. There is some data sources out there that display the location of wells throughout the United States. However, these miss a time component, which is extremely important for epidemiological studies. So here again, is this satelliteable? Because there's a policy and health implications here too. The better understanding of the health consequences of pollution emitted by this type of infrastructure can inform local siting setback policies that establish a minimal distance from residential areas for development of new fossil fuel infrastructure. This has important environmental justice implications because hazardous and polluting infrastructure is frequently developed in proximity to communities targeted for marginalization. I know that emissions from fossil fuel is also being discussed at the other session, but is this satelliteable? One of the, after extraction, there is processing. And one of the most, that also releases pollutants, and one of the most well-known examples of this is the Louisiana cancer ash. The EPA National Air Toxics Assessment data has been previously used to evaluate pollution from these sites, which also include the Houston Ship Channel that was impacted by Harvey. But is this satelliteable? Because here again, there is a huge environmental justice issue with individuals from communities targeted for marginalization who have been closer to this problem, leading resistance to new fossil fuel infrastructure, such as the Formosa plant in Louisiana. And these efforts would improve health of the entire population. Our research can contribute to the evidence base that's used and needed for environmental reviews and impact analysis that are conducted for local zoning and siting decisions, such as this one. Then we don't have time to go through all of these, but I did want to mention waste. We talked about waste from fracking already, but coal processing, coal burning power plants also produce waste. And it's called coal ash, a catch-all term that is used for all waste from coal, from burning coal. And these contain arsenic, chromium, lead, mercury. Coal ash is usually mixed with water and is stored in these coal ash ponds, which have a tendency to leak, flood, and spill, sometimes in catastrophic amounts, which you might have seen this infrastructure when your plane was landing here. These polluting industries are frequently located in proximity to waterways where the byproducts can be disposed of. I hear that satellite data is already being used to identify algae blooms, which are becoming more frequent with our industrialized food systems. So here's my last question. Is water pollution satelliteable? That's it. Thank you.
Hey, thank you. Our final speaker is Andy Sayer, the NASA Goddard Space Flight Center and University of Maryland, Baltimore County, UMBC.
Hi, everybody, and hi, everybody online. I want to talk a little bit about who we are, where we're coming from, and where we're going with PACE. So I've got 4 names on this title slide. There's me, Andrew or Andy Sayer, and Kirk Noblespeaks are the first 2. So my responsibility is algorithm development from the imager on PACE, OCI, So aerosol and cloud retrievals. HAQAST is the same, but for the polar emitters. So our jobs are turning raw measurements, radiances into geophysical data, aerosol products, cloud products, everything else. The last two names, Natasha and Erin, they're our applications leads. And their job is kind of connecting the user community with us and with science team members, raising awareness, helping you do all the data analysis. And it's thanks to those two twisting Jenny's arm that I'm here today. So thank you for being amenable to that. Okay, so between this next 10 minutes and my poster yesterday, which you all came to, you're going to be experts on PACE very soon. Okay, so I was born and grew up in Scotland. It's a bit of a joke, but Scotland really is always cloudy, top half of this image. I also like to be outside. Sometimes that's a bad combination. And as a kid, I had to get used to predicting how long have I got before this starts raining and how fast can I run home? So now I guess I started off doing this ground-based remote sensing, and now I'm doing satellite remote sensing. So it's all connected and probably inevitable. And although the air quality in the UK is pretty good, sometimes bad things happen. Also in this image right here, this is from the Buncefield oil storage explosion in December 2005 in a very densely populated small country like the UK. This kind of black smear affects a lot of people. I actually left Scotland at this time, was living about there. That's not great. So there's more than 10 million people in Greater London. So, you know, we do unfortunately have extreme events there too. So I've had the good fortune to work on a lot of US polar orbiting satellites over the last few decades. Everything which is in dark blue here is a data set which we've released. A lot of this is being used by Yang, by Randall, their groups and others, turning the aerosol retrievals into PM estimates, and then a bunch of the rest of you are all using these in your analysis. That's really wonderful. Everything which is in a light blue is something that we hope to be able to make available. So this includes AVHRR. We could go all the way back to 1981. So we could see a lot about how the world was back then, how things are changing. If you happen to be reviewing our proposal to do this, please fund us. We've been trying several times. Also, coming in the near future, we know Terra, we know Aqua, they're going to go offline. They've done really excellent. They're way past their design life. Now, Aqua is, in a sense, being continued by VIAs on various platforms. We're processing that. In the morning, however, it's a different situation. The US has got no follow-on for Terra at all. It just doesn't exist. Europe's METOP second generation should launch in 2024 as well. That will have similar instruments to what we've been using in the US. So I would really like if NASA, maybe this is a headquarters question, can see fit to make sure we have some funding to put our algorithms and avoid this totally avoidable data gap. But also joining this record next year, which we're very excited about, is PACE. So PACE is a real mission. The name stands for Plankton Aerosol Cloud Ocean Ecosystem. So some people say, oh, it's an ocean sensor, but no, the atmosphere is literally half of the name. The satellite exists. This is us here. I'm one of these. You probably can't tell which one. I can't tell either. It's been fully built. It's being tested. Everything's been calibrated, characterized. It's being vibration tested and thermal vacuum tested right now. It's going to launch in January 2024, unless weather or something pushes it a bit. PACE has got 3 instruments. One is the OCI, which is a broad swath hyperspectral imager. I think it was Rob's slide said it was like OMI and MODIS combined. That's a pretty decent assessment. The other 2 are multi-angle polar emitters, which are very information rich. If you know polar data, which flew as part of the A-train, kind of similar to that, but higher resolution and higher fidelity. We've got these 3 different sensors and they all provide air quality relevant data. So the imager OCI, we're going to be able to extend and improve on our heritage types of aerosol products. This is a satellite image from the Australian Black Summer fires from, I think it was January 2020, this image. We've got a true color image. We've got optical depth. So redder is more aerosol. we've got angstrom exponent. So bluer is kind of dominance by smaller particles, smoke. And then in the pink here, very coarse, this is the OMI ultraviolet absorbing aerosol index. So pinker colors mean more aerosol, more absorption. With OCI, we can do all of this, except the UV data will be on the same footprint, the same spatial resolution as the rest. So we can get this again in much finer scale. You won't have to manually match up different sensors. It'll be recorded simultaneously. And we can use this capability to go beyond heritage. This is a slide from Lorraine Raymer. Many of you know she's on the PACE science team. They've been extending their heritage dark target algorithms that Rob talked about to include these UV capabilities. And with this, they can also quantify aerosol absorption, and going forward should be able to quantify aerosol layer height as well. So you can tell, is this in the boundary layer? Is it up high? It's obviously very important for air quality stuff. This is a case study they have of a dust storm through the Caribbean. We've got 4 AeroNet validation sites on this. And here we've got some plots showing the aerosol loading and the aerosol absorption, and the different colors at the different sites. And the main point is their algorithm, it can capture the spatial gradients and the spectral dependence of the aerosol signal and the aerosol absorption. So again, much enhanced aerosol typing capabilities compared to what we've got now. And it will be at 1 kilometer pixel size globally in fairly decent latency. So as a warning, the next slide's got some blinking GIFs. So you'll want. Okay, so the other 2 instruments are multi-angle polar emitters. Those are both important words. Multi-angle means we're going to see the same spot from different view angles over the course of a few minutes. And I have this image from the HARP CubeSat on the left of a scene off the coast of Africa. So as it steps through the various views, you can see there's differences in brightness, there's differences in color. You can see objects like clouds move due to parallax shift. So this is a whole bunch of different dimensionality of information, which tells us more about what's in the atmosphere and what's on the surface, and also where it is. On the right-hand side, this is an image of the NASA Ames car park taken with a normal camera and then with a camera with a polarized filter over it. So these instruments are going to be measuring radiance and polarized radiance at multiple angles globally. And again, the fact that the intensity and the polarized images look different tell you there's information in the polarized signal about what you're looking at. And again, this is similar to what Polder did, but we're going to do it at more view angles with a better polarimetric accuracy and a finer spatial resolution. So again, going quite a lot beyond what's been done before. This will tell you more aerosol composition related information such as size distribution, again about absorption, sphericity, so it's better aerosol type discrimination, aerosol height too. And there are ways to get involved before PACE launches. We have an earlier adopter program. Daniel Tong, I don't know if he's here or upstairs right now. He's one of our earlier adopters. And this is a program which is designed to help get you proxy data, get you familiar with the sorts of data sets we'll be providing, connect you to science team members so that when PACE does launch, you can get your applied science going as quickly as possible. It's also a forum for you to tell us, hey, I really hate this about the existing products, can you change it? And then, you know, we have flexibility with before launch. So if you tell us you want something different, we can, you know, see if that's reasonable and try and do it. And finally, beyond just early adopters, there's a whole range of other ways you can get involved. The early adopter program is now being expanded to what we call the community of practice. This is run by Natasha and Erin. We have monthly telecons which showcase science team activities, give you mission updates. There are ways to get funded to work on PACE, the PACE Science and Applications team. We expect a NASA Rosa's course sometime late this round or else coming out February 24, just after launch. And there's also a community of potential, which is for people who say, hey, I think this sounds cool, but I've got no idea. Can you give me some help? So we're really, we're trying to provide lots of resources to get users of all levels engaged. And again, if you think this isn't for me or I don't understand this, please tell me why so we can go to management and fix the problem. I'm probably a bit over my time, but thanks very much.
Okay, thank you. Andy, stay up here. Now we're going to have our panel. Please come. Take a seat. Okay. Okay. So I don't know if we have questions online yet. Check.
Yeah.
Oh, yeah. Okay, so let's take a few questions from the room. Okay, Brad Pierce.
This is to Leticia. So you were talking about looking at oil and gas emissions and their association. Have you looked very much at the VIIRS day-night band and their characterization of persistent anomalies that are basically these oil and gas refineries?
So I just learned about that on this meeting and cannot wait to look at it. And I anticipate that we can probably see these flaring events at night. And then I'm hoping that with some of the new satellites, also be able to measure some of the more of the pollution or the gases that are known to have health consequences, like formaldehyde and some of the other ones. It's from a health perspective, having worked with the public health researchers, that is definitely going to be a question we get whenever we submit it to a public health journal. So having a better understanding of not only the flaring events, but the gases that are around it as well is going to be super important for the health question.
And I think Chris is here, at least he was yesterday. And because they're doing multispectral characterization, they are able to say, you know, this is a ferrous metal plant. This is a flaring event. This is a downstream process. So they actually can get a lot of detail that I think would be very useful for your work.
Thank you. Yeah, I'm so looking forward to working with that.
I'll just give a shout out. Unfortunately, with the parallel sessions, we can't go to both, but with the oil and gas panel is happening right now. So there will be recordings available.
For the multiple satellite blended data product, I guess I have kind of a twofold question. The first is how long, once the data is available from the different satellites, does it actually take to run, let's say like for a day, if you were to like upkeep the algorithm? And then considering like we've talked about that the MODIS satellites are going down at some point, how flexible it is as far as like changing in and out different satellite products.
Okay, that's a good question. So in terms of at least the way we imagine this is we are kind of running same algorithm on multiple satellites. And it's very quick. So I mean, as long as the data is there, it can be run pretty much immediately. And you know, within it just depends on access to data in this case, but it can be done in basically near real time. You know, so maybe that definition is 30 minutes, that kind of thing. You know, that kind of time scale, it can be done. In terms of the other question was related to flexibility. So flexibility wise, I mean, again, there is some work that has to be done, but as long as the sensors have the same kind of capabilities, you have to create new lookup tables and do things like that. But the you know, kind of the standard, it can work with fairly easily.
Thank you.
Okay, I'm holding it.
Are there any other questions? Martin.
This is for Andy. I enjoyed all the compelling imagery about pace, and so I did a quick look online to see what I could find on the website, and saw the spectral aerosol optical depth So what I'm wondering is, you described some advanced capabilities. What's your timeline on the unfolding of those capabilities and when those data might be available? And if there's certain places that we should be looking for?
So it's a good question. We have a requirement on headquarters to be considered a success, which is it launches around January the 9th. It takes about 2 months to go into operations mode, and then it's within 60 days of then we should be generating products routinely. The required products include spectral optical depth and fine mode fraction over ocean. We've already implemented the deep blue and dark target heritage algorithms. Lorraine Ramos' approach, she wrote to me on Friday and said she's about to deliver the code. So hopefully that would also be available fairly soon after launch. The polarimeters is a bit of a different story. They are more computationally expensive. A lot of them still can be run in roughly near real time, but because we've had many approaches proposed, it's going to be dependent, I guess, on the PI's code delivery and on user requests as to which ones get processed and when we start doing that. Alexei Leopustin is also applying the MAIA algorithm to PACE. He also is going to deliver code soon, he says. So depending on definitions of soon, is 8 months enough? It could well be all roughly at launch, but we know for sure at least deep blue and dark target because it's already implemented.
Okay, next question. Can somebody check if there are questions online? If not, I came prepared with a list of questions. So if you want to hear my questions, I can do that, but I'd rather hear you all ask questions first. Okay, Chris.
Great presentations. My questions, I guess primarily for Yang and MAIA. But essentially, I suspect, I'm just curious if the other prime, sorry if I get the wrong phrasing, health teams will be also able to look at a wider range of health outcomes? Or if that was the design strategy targeted towards specific data sorts that as opposed to both the short and long-term ones on purpose, or if you anticipate that would be expanded?
You mean the health effect studies?
Yes.
I think the PM products will be publicly available. You can do whatever study you want with the product. The reason that we have teams attached to the mission, teams of epidemiologists attached to the mission, is to make sure the product design actually reflects their demand in terms of revisit frequency, spatial resolution, uncertainty requirements, and all that. They were all worked into the algorithm. And similarly for the STA, the secondary target areas, they were mostly suggested by the user community. I think that you can do whatever you want with that, right? MAIA is going to make one set of PM products based on one set of algorithm. But all the ingredients to build a PM product will be available. You can do your own retrieval of level 2 and level 4 PM products, right, to suit your own need. And you can go from there and any kinds of epi study you want.
So this is kind of to the whole group. I really liked Rob's presentation of, this harmonized retrieval for sort of these broadband visible spectrometers. And it's great to hear that both deep blue and dark target are going to be part of PACE. But again, between PACE and MAIA, you've got multi-angle imagers to me, it's also important that those two are integrated and there's some common approaches in terms of that. How much is there in terms of conversations between PACE and MAIA on that?
Candidly, not a huge amount right now. They are funded by NASA in their wisdom through separate calls. So it's kind of up to individual PIs to submit to both calls. We've got, I think, 4 or 5 candidate polarimeter aerosol retrievals for PACE, which have been submitted. In principle, I think those could all work on the MAIA polarimeter as well. I'm not sure how many different algorithms are part of the MAIA team. Okay. Is that Fengzhu's or?
Yeah.
Okay. Yeah. So we've the Fengzhu from Oklahoma, who's Young says is funded for that. He's not part of PACE, but we have been talking with him about his code.
So I think, so that with MAIA, you've got these 11 tier 1 sites that you're going to be doing the full retrieval on. 3 of those are in the US. So for this community, if you can link what you're doing with MAIA to PACE, where presumably you'll be able to have multi-angle retrievals everywhere, I think that'd be really good for the community.
Yeah, I mean, that makes a lot of sense, Brad. I think so far the intermission connection has been limited. I guess at the very beginning, we didn't anticipate a substantial overlap in terms of on-orbit times between MAIA and PACE. And now we do. I think Olga is on PACE, right?
I think she could be a co-ion.
Right. So the multi-angle algorithm has the MAIA legacy. So there is a lot of common ground to missions to work together.
Hopefully NASA headquarters hears that message too.
We have NASA headquarters representative here.
That's what-
Hey, Randall Martin.
I wanted to build upon a challenging and perceptive question that Andy asked yesterday. While there's 3 experts up here about the information content that is available at 1 kilometer resolution for PM 2.5, and we have here missions that are designed to push resolution. MAIA has it as a stated product, and I'm wondering if the 3 of you could speak about that level of information content and how we can push that forward, especially over urban areas, I guess is the key challenge to bring in, where there would be irregularities and surface characteristics that will affect that scattered sunlight.
I can take the first cut. So MAIA's raw pixel size is between 250 meters to 500 meters based on the different bands. So it does have a bit more information to actually retrieve at 1 kilometer resolution. And then if you think about the raw information coming out of the MAIA instrument as 14 bands, repolarimetry channels, and expansion into UV and near infrared, there's a lot more information to make that retrieval. So I think MAIA is more like a information-rich mission for a limited set of locations. I mean, it's designed to be an EVI mission. It's not. It's kind of exploratory.
So I think a bit to satisfactorily solve some urban issues, you need to move away from the historical paradigm of single pixel processing and make much more use of spatial and temporal constraints. So the big challenge is always you look at the Earth from space, you mostly see the ground. So how do I parameterize the reflection, its spectral, its angular dependence sufficiently accurately that I can take the small fraction of the signals from the atmosphere and find out what's there. Now, MAIA's fine spatial resolution, that's great because it means there'll be far few pixels which are heterogeneous, contain, for example, mixed water and land. PACE's polarimeters, the native resolutions are going to be more like 2.6 kilometers and probably projected to a common 5.2 kilometer grid. OCI is about 1 kilometer, so similar to MODIS. So there will be some mixed pixels. Now, I would say over the last decade or so, Alexei Leopustin with his MAIA algorithm, the temporal compositing he's done has meant he's been able to get away with making fewer assumptions about surface behavior than, for example, Rob's algorithm or Deep Blue. And that's great. That reduces the artifacts. The multi-angle polarimetric aspect, I think, will help further because you still have got some, all these service models are kind of empirical or semi-empirical. They assume some effective reflective medium. They assume it's made of some combination of a flat surface and tall boxes and little short boxes, right? So the fewer kind of assumptions you have to build into that, the more realistic you can get. I honestly, I think we're coming to the point now where it's getting hard to tell what's an artifact and what's real, partially because we don't have ground truth data on the spatial scales needed to say there's been a very small number of intensive field campaigns. The US has done a bunch called Dragons with distributed regional aeronet something network, where they put a few dozen sun photometers over across a major urban area. I think we need more of those. You can get handheld instruments, they cost a few $1,000s, or we have a few dozen that you can borrow. It would be great if we can get a bunch of people to say, every day this week, just go outside and point at the sun, and then we could build up some really fine scale evaluation of a total column and kind of nail down these questions. Just a long way of saying that fundamentally, I think we can do better, but it's still really hard to know how well we're going to do because there is not fine scale ground-based validation for the total column.
And then, I mean, the other thing that we can think about is, of course, the temporal. So when he's having the geostationary, the spatial resolution isn't quite there yet. Because it's 2 kilometers, 1 kilometer at best for the ABIs, for example. But you do have time changes, so you can very quick time changes, and won't the actual surface is not going to change too much from the morning to the afternoon or anything like that with rains, which is But the hard part with our retrievals is that going into these geos is kind of a world we've never gone to before, and the sun behaves very differently. So you recognize something like MODIS. MODIS has looked at the globe at 10:30 or 1:30 p.m. forever. And so a lot of long-term composites about the surface have been created. The geo, now you have, walk outside, look, the world looks very different at 6 p.m. than it does at noon in terms of shadowings and especially in urban areas, buildings and everything else like that. So it's active research. But yeah, that's where we need to go, obviously. So.
Okay. Did you want to say one more thing?
Yeah, something to add.
Okay.
It gets a little philosophical here. Just from the optical retrievals to the surface PM retrievals, the operational algorithm of MAIA does not have any strong spatial autocorrelation or temporal autocorrelation built into it. It's essentially a pixel level retrieval or pixel level translation. And my idea going into the design is that the assumption of spatial continuity or temporal continuity of PM is a rather strong consumption, especially in the urban environment. And then in natural disaster situations like wildfire, dust storms, they are inherently discontinuous in space. So I think the algorithm will evolve. And what I like about MAIA in particular is it's kind of an open-ended mission. All the ingredients are provided to the super users. You can build your own algorithm. It could have many different versions of level 4 PM products out there. Like MAIA is only there to provide one basic, good enough solution. So I think it suits the rapid evolution of this AOD to PM field because it's moving so rapidly into different types of tech, all of which can be accommodated within sort of this framework.
Okay, that's a perfect segue for my first question. And I want to bring it back. I want to hear from Leticia first and then you, Yang. I want to see you squirm, Yang. Okay. So as you know, most of the people in the public health community, they're what you would call the community of potential. Only a few are using satellite data, the vast majority are. Okay, now we have MAIA coming up. Here's my question. What would MAIA have to demonstrate to convince the health community to adopt satellite data more broadly?
I know the answer.
If you can let Yang squirm first if you want. It's up to you. You can go first, but okay.
So I've been in the school of public health for 14 years. What I learned is that public health people are the most self-critical yet flexible and people I have ever met. And the mentality, this can-do mentality is unparalleled. You throw something at them, they will make it work. So there is no barrier to adapting satellite data. What they always ask me is, where do I get it? It's that. So I think it's great.
That was so sweet. Okay. So I think that it's almost reversed. The problem with public health data is patient confidentiality, health confidentiality, and being able to get that information that has a time component and has a health outcome, and it is geographically granular enough. We don't get 1 kilometer resolution, we get zip code, right? So that is a lot of times the rate limiting step, because you can have a very good relationship with your state health department and get some of that information through some of the health registries, but that's one state. So then you don't have a big enough sample size. So that's some of the things that we have been talking about. And the way I actually met Yang is I found this amazing data that I could never process on my laptop. So I think that building on the computational power that NASA clearly has, to then, hey, here is a list of addresses. What can you get me from your computational power? Because there is no way we have that. From the public health perspective, is really where the bridges are necessary for us to use satellite data more, because we usually get very poor data, and we've been trying to use it in every single possible way, and then having the computational power and the access to large health data sets is really the rate limiting step. I had a question that's kind of segue to both of them. And it's coming from what you were saying, to get everybody outside and point to the sky, and how to calibrate the satellite data. And with our work at the American Cancer Society with different communities, and also as part of my work with the Moms Clean Air Force, maybe it's to you, John, does NASA has any citizen science or any efforts that get children or any school age to participate in? I can only imagine, like, we had the most lame efforts, and kids are all over it. If you said that they could help calibrate a satellite, you probably get every kid outside doing that. And then, air monitors, as you're doing in your community, and some of the other things. And there's a lot more funding now for citizen science and the community-based needs. So I was wondering if there are any of these types of efforts, so that it goes both ways, that we consume your satellite data, but we also are helping calibrate or make it better.
Yeah, the primary one that comes to mind, I'll let Laura chime in too if there's some others, but when you're talking about elementary or middle school, children globally is the NASA GLOBE program, so aptly named, where it's, I've forgotten, it's thousands of schools, I think, that are involved. Anybody can be involved.
Doesn't have to be schools. You
Yeah.
can download the app.
That's true. In today's day and age, yes, it doesn't even have to be a physical school, but it's of course a virtual and a physical presence where they have a lot of schools that not only participate in, educational programs about the Earth and how it's changing and what we see from satellites, but they also provide their own data from their own weather stations at their schools that they have and the kids monitor and things like that. Well, also they take pictures and upload them to the GLOBE website of clouds, what clouds they're seeing that day. Also, there's a part of GLOBE that is called a mosquito mapper, where not just children, but anybody can take pictures of mosquitoes that they see or they catching in their houses. So we know what different species of mosquitoes are. They have a lot of different facets to it. But that's the primary one that I know of aimed at younger children.
That's the only one I know of. I don't have anything else.
Okay.
You described the GLOBE program.
You're headed, Kirk.
Okay, but Leticia, you were saying very clearly that level 4 products, these products that would help the health community use the data, access it without having to process it themselves. That's NASA calls this level 4. So it's a data product that developed explicitly for your community.
We're heading up again. There is also a variety of citizen science projects that NASA's done. I was part of one of them. One didn't specifically do schools, it more specifically did at people in the community that said, hey, we want to have an instrument, let's put it on our house. And the little map I showed, which was like related to the Quantico fire, wasn't part of one of the networks, but that kind of inspired me when that day happened in our neighborhood that, oh, there's smoke. So it was the kind of thing that we were after from the citizen science by having it at the ground at high resolution, having satellite at high resolution together. So,
Yeah, I'll just add one more thing to that. And you reminded me, Rob, of a project that was very successful that was completed a few years ago, 2 or 3 years ago, in cooperation with NOAA. That was an air quality / health / water quality project. Richard Stump from NOAA was the lead. It was with the state of Florida and NOAA to look at harmful algal blooms off the coast, off the Florida Gulf Coast. Not only from a water quality issue and tourism issue, but also the toxins that aerosolize from these harmful algal blooms cause a lot of respiratory distress. So they wanted to make an online system at NOAA where people could go beach by beach along the Florida Gulf Coast and get a respiratory distress forecast and harmful algal bloom forecast for the next 48 hours. Most Marine Laboratory in Sarasota was one of the partners, but the problem is, they can only sample and validate with their limited staff, every beach after X number of days before the rotation comes around again. And so they developed something called HAQAST, which was a special mobile filter that you could put on your smartphone. And they employed all the lifeguards and people to take samples of the water every day at a certain time. It took a picture of the water sample, sent it to most Marine Laboratory, which they could then analyze for the presence of harmful algal blooms. And so that led to this basically near real-time forecasting system, thanks to citizen science as well.
Is there one online? Should we resort to my list here? Okay. One more question here. Oh, okay. This is thinking really far ahead. Okay. So I've been on a number of proposals with health professionals, and I'm always just wide-eyed at their budgets that they're requesting. When I write a NASA proposal, the budgets are much smaller. Okay. So just thinking about the role of satellites in the private sector down the road, especially given NASA's effort to form public-private partnerships, do you think that there may be a role for privately funded health-based satellites in the future?
Say it again.
What I'm saying is, will the health community actually pay for their own satellite? Well, we have EDF, they're doing it, they're putting up a satellite. Why couldn't the health community?
The EDF, and they've actually, some of the people I used to work with at Goddard, they're now doing the algorithms for that. And I think it's great that these non-states are able to do it. What I've been trying to keep an eye on all the I forget the name of the program, commercials, small sat data acquisition. One of the challenges with that is for the retrievals to be good, we need to know the radiometric calibration and the spectral response function very well. Some of the companies don't want to tell us that because it's proprietary, but if they don't, then you can't do much more beyond pretty pictures. Yang maybe has perspectives on it because I feel maybe MAIA is a step towards that, right?
Yeah.
Yeah, but
If you don't have an answer, don't worry. I was being more of a jerk here with this question.
it's a very
But I'm curious about it, honestly.
interesting thought. I think currently launching a health-focused, affordable satellite mission is still not being considered an option by like everyone.
Yeah.
But if it takes $10 to launch a kilo of payload into low Earth orbit, that makes the idea a lot more fascinating. Like currently, I think when I was a grad student, it's $1 million to launch a payload. With SpaceX, I think it's $5,000 a launch of a payload. When it comes down to maybe $100, you see epidemiologists design their own satellites.
This really went back to my first question of what I was asking, what would it take to convince the health community that the satellite data are very useful for their applications and for them to adopt it more broadly to their community?
Here is a related comment. Does that work? I think that maybe what we can do better is partnering in these funding opportunities and in our shared interests for satellite data to start capturing the type of exposures that we know have health consequences. Formaldehyde being one of the very first ones we discussed, benzene, and to have better measures of those so that we can have a better understanding of the health impacts of exposure to those have then can inform policy and rules. So that I think is where the missing or the overlap is still not there. Is the satellite data measures what I know now more about the optical properties of gases than I ever knew anybody could know. And that's what satellites are measuring, but it doesn't mean that those are the gases that have health consequences. So I think that that's where the great opportunity for this type of collaboration might be.
Okay, we have a question online.
It's more of a comment. Malcolm Zachariah says EPA is related to the previous conversation. EPA had a sensor validation calibration project for different environments. I don't remember the name, but there was a college student who worked with one of our agencies, the Oklahoma DEQ, monitoring sites to co-locate the sensor with our regulatory equipment. And yeah, just thinking of that with Yang's point, you know, there's definitely people in the health community who are building their own low cost sensors. So maybe satellites are next.
Okay, we have 5 more minutes. I don't think anybody wants another one of my questions. I still have one left. Is there one from the audience here? Another question? Okay, we have one in the back.
Question for the algorithm guys. So we have a several-fold increase in the volume of information to process, and also several-fold of dimension of information for each record as well, considering the increase in spatial temporal resolution and the multi-angle polarization information that you get. And what's the plan or what's the strategy of keeping it operational in the algorithm development? Thanks.
To be honest, I didn't quite hear the question all the way.
So the volume size.
I wonder if your mic was on.
Sorry, the satellite data volume size has increased massively, and it's going to increase, of course, in the future. And what's the plan of keeping your algorithms operational?
What is the plan
Keeping
for
the product operational, fast and accessible.
How do we run operationally when we have high dimensional data? That's, I think, work in progress, I think, in that regard. I mean, the way, we can think about doing retrievals and such from individual sensors, which is the way I've done it, which is the lowest hanging fruit, right? Then it gets, more complicated if you want to use more and do, more sensor fusion, then it gets more, if you were using data from 6 different sensors to create one product from the gradient space. I'm not sure if that's quite what you're asking though. Maybe you're better. I'm just not sure what I think part of it too is I think as it was talked about too with this, kind of an as in a transition, I guess, to, how data is put together and served through open science, et cetera, like that too. So, more data will be in the cloud, more data, so there's all that kind of thing going on too. So as there becomes more and more data, it will also become more and more available, I guess, too.
So the slowest part of the retrievals is radiative transfer. So the bridge between what's measured and what you want to find out. Traditionally, people deal with this 2 ways. The first is they can run radiative transfer codes in forward mode, all the time. That's very accurate, very time consuming. The other way is you build lookup tables where you pre-compute things once offline, and then you read this into RAM. That's faster, but still time consuming. And the disadvantage is every dimension you add, things get an order of magnitude more complicated. So with the polarimeters, what's being done is replacing these more or less with neural networks, which are trained on radiative transfer simulations. They're a lot faster than interpolation. You can kind of train until it's sufficiently accurate. So it kind of just moves the burden of the calculation outside of the processing pipeline. So code efficiency and code portability, because if you need less RAM, you can run more stuff in parallel. That combines with what Rob mentioned about things are going to the cloud. I think we're still figuring out how that's going to happen, and there's going to be some kind of concerns then if we're being billed each time we run a piece of code as opposed to being billed for buying a computer. So we'll see how it shakes out. But I think an advantage of that is if you suddenly do say, hey, I really need this much resource, then Amazon, these other companies, they have it. For PACE, we have the hardware to process everything that we're required to process in-house really pretty quickly. The bottleneck's getting it off the spacecraft. Looking ahead beyond PACE, as other missions like AOS come online in 10 years, I'm expecting that it's going to be entirely in the cloud, but we'll have to wait and see.
Hey, we're actually at the end of time. So the panelists are spared my other question, my last question. So I think we're at the end of the meeting, right?
I just want to thank all of our panelists, everybody who's been attending, everybody who spoke at this meeting since this is our last public panel here, everyone who's been involved in organizing. It's not just me, the whole team. It's been a real delight. So thank you all for being here at HAQAST.
Randall, would you like to say something inspirational, maybe? Since you're hosting.
Honor to host you. Thank you.